go ahead and get started with today's webinar on sustainable phosphorus and manure management. I'm Matt Schultz with the Sustainable Phosphorus Alliance, joined by Olga Borquez and our panelists today, who I'll introduce here in a second. So a little bit about the Sustainable Phosphorus Alliance. We're a member organization, and we work to advocate for the sustainable use, recovery, and recycling of phosphorus in the food system. We're supported by a great slate of member organizations, and if your organization would like to become a member to help support webinars such as this, please reach out to us at phosphorusalliance.org. We'd be happy to talk to you about that discussion. We don't have memberships for individual people, just for organizations, but we'd be happy to talk to you about your organization becoming a member. We also run an annual event called the Phosphorus Forum, and the next one's coming up next month. And so that's happening in Raleigh, North Carolina, September 17th and 18th. We've got a really great agenda, and you can find that at the website for the event, which I should have put up here, but didn't. However, if you go to the phosphorusalliance.org website, or I see Olga just put a link into the chat, you should be able to register for that. There aren't many seats left, so I wouldn't wait very long to do that registration if you're interested in coming. You can at least see the agenda there and see if it appeals to you. So I also want to acknowledge the second greatest phosphorus conference that's happening, which is the Sustainable Phosphorus Summit. And that's happening in Ghana next month, starting September 30th, going until October 3rd. And the registration and full program are available at this website here at upcyclelakes.org. This is a great event. If you can make it, Ghana will be a pretty cool location. It's happening in Accra. And this is an event that happens every 2 years on a different continent and deals with phosphorus sustainability issues. So it's the first time it's coming to Africa. And if you're interested, I certainly encourage you to go to that as well. So with that, we can talk about today's webinar and the unsavory topic of today's webinar, which is managing manure in the best way to avoid overloading our water bodies with phosphorus. As we'll hear, this is a major concern in the phosphorus sustainability world, and perhaps the major concern across watersheds in the US and beyond. So we're going to talk about the scale of the program, of the problem, and the solutions available. As always, we have a great team of panelists assembled today, and I want to thank one of them, especially Dr. Mahmoud Sharara of NC State, who helped put this team together. I'm going to read abbreviated bios for each speaker at the top of their presentations, starting with our first speaker today, which is Dr. Jerry Sherson. He's best known for his extensive research on the benefits and limitations of corn distillers' dried grains with solubles, but he also works in the areas of determining the nutritional value and characteristics of rendered animal byproducts, organic food wastes, and using food and agricultural wastewater streams to produce microalgae for animal feed. And Jerry, if you're ready to go, we can go ahead and start with your presentation.
Well, thanks, Matt. Hello, everyone. And I want to begin by emphasizing that, much like what Matt just mentioned, that we have a big phosphorus management problem. And this problem is associated with the concentration of a large number of livestock and poultry farms with high animal density in many regions of the U.S. And this results, as you might expect, in the production of large amounts of manure, which phosphorus is a major component. And this manure is generally applied to cropland in amounts that are much greater than what the crop nutrient uptake really demands. And so as phosphorus accumulates in soil, it can lead to runoff from soil erosion, depending on types of conservation practices that might be used. And this phosphorus can ultimately, of course, lead to eutrophication, algae blooms, and fish kills, as I've shown here in this slide. From a global perspective, we desperately need to improve phosphorus utilization efficiency in agriculture and food production systems because phosphorus, along with nitrogen, is one of the 6 planetary boundaries that's been exceeded. Now, for those of you that may not be familiar with planetary boundaries, these are defined as the limits of our safe operating space that should not be exceeded in order to avoid irreversible environmental damage and destabilizing the Earth's ecosystems. I think we also need to remember that phosphorus is a finite resource that will be depleted within the next 30 to 40 years unless we do more to conserve and recycle it for productive purposes. Agriculture and food production are major consumers of mined rock phosphate, and unfortunately, only about 15% of the phosphorus that is extracted from nature ends up in the foods that we actually consume. So 85% of that phosphorus is lost. One of the reasons for this is that phosphorus utilization efficiency is poor and highly variable in livestock and poultry production systems, both at the individual animal level and at the farm level, where the efficiency of converting the phosphorus in animal feed into phosphorus found in meat, milk, and eggs generally ranges from about as low as 14% for beef and dairy, some of the estimates, to as high as 60% among different animal species. So as a result, the focus of what I've been asked to talk about today is really the connection between animal feed and manure uh, as major drivers of environmental sustainable livestock and poultry production systems. In fact, about 42% of the life cycle loss of phosphorus from U.S. food production occurs from livestock manure and runoff, and our phosphorus management problem has only become worse over time, where historically, as the concentration of animals on individual farms has increased, and as the number of these concentrated livestock and poultry farms have also increased since 1930, the amount of manure, phosphorus loading in these agricultural soils has increased by more than 70%, as shown in the red shaded areas across the United States in this map. Cattle are the major contributors to manure phosphorus in all parts of the U.S., with swine shown here in pink in the Midwest and eastern North Carolina, and broilers shown in blue uh, in some of the southeastern states as major contributors in those regions. And these concentrated livestock and poultry production areas are major environmental concerns because the amount of manure phosphorus being produced and applied to soil near these farms has exceeded crop uptake and the environmental capacity to absorb and neutralize it without causing ecological damage in many areas of the Midwest, the Southeast, and parts of the Southwest. So as a result, the nitrate and phosphorus runoff from farmland into our streams and rivers that feed into the Mississippi River system has resulted in nitrate and phosphorus loading in the Gulf of Mexico and expanding of the dead zone as we know it. So this brings to my focus today, and that is to help overcome this problem, we need to understand the role of animal nutrition and the challenges and solutions for reducing phosphorus content in manure at the farm level. And I want to go back to the basics where fundamentally animal nutrition is relatively simple. It's the execution that sometimes gets us into trouble. In feeding livestock and poultry, our goal is to meet the daily requirements, and these are amounts of nutrients per day, of all essential nutrients to optimize animal performance, while at the same time minimizing overfeeding and underfeeding of nutrients. So the daily amounts of digestible nutrients required by swine, poultry, beef, and dairy cattle are pretty well established, and we have several guidelines that nutritionists use to formulate diets for these different species. And so if we know the daily feed intake of an animal and under specific farm conditions, we can easily calculate the dietary concentration of digestible nutrients such as phosphorus, that are needed in the complete diet to optimize nutrient utilization efficiency. Nutritionists routinely formulate swine and poultry diets on a digestible or available phosphorus basis. However, the two most common feed ingredients that we use in U.S. animal diets are corn and soybean meal, which contain high proportions of phytate, which is the indigestible form of phosphorus that causes the total phosphorus in these ingredients to only be about 34 to 48% digestible. In comparison, corn distillers grains with solubles, which is a byproduct or co-product of the U.S. ethanol industry, is the other main ingredient that we use in swine, poultry, dairy, and beef diets as well. And it has the advantage over corn and soybean meal because it contains a lower proportion of phytate relative to total phosphorus content, which makes distillers grains a better source of digestible phosphorus than corn and soybean meal. Fortunately, we can overcome the problems in swine and poultry diets with corn and soybean meal with the use of commercial phytase sources. Um, and these phytase enzymes are cost effective, they're commercially available, and you can see from this graph that as we increase the dosage, we increase phosphorus digestibility, and it does vary somewhat among the different commercial sources available. In fact, one of the emerging diet formulation strategies to reduce both nitrogen and phosphorus in manure from pigs and poultry is to reduce the amount of excess protein or nitrogen in the diet by reducing the amount of soybean meal that's used and adding synthetic amino acids to meet the pig's or poultry's digestible amino acid requirements. And at the same time, add phytase enzyme to improve phosphorus digestibility in these corn and soybean meal-based diets. And if we use this practical feed formulation strategy, we can reduce nitrogen excretion in the manure by about 28% and phosphorus excretion by 54%. And this is an example for growing finishing pigs without any adverse effects on growth performance or carcass composition. We also know that different supplemental inorganic phosphorus sources that are commonly added to swine, poultry, and cattle diets to some extent vary in phosphorus digestibility and water solubility. So, in fact, results from a study that I'm referencing here from 2020 show that whole farm phosphorus use efficiency is actually improved if we use mono-dicalcium phosphate as a inorganic phosphorus source instead of dical, because mono-dicalcium phosphate has about 18 and a half times more water-soluble phosphorus than dical, and that results in greater phosphorus digestibility. A lower amount of supplemental inorganic phosphorus is needed in the diet, and it also results in about 38% less phosphorus in manure and greater crop phosphorus uptake. So choice of inorganic phosphate sources is an important consideration as well. So therefore, we know how to formulate diets to reduce manure phosphorus content, and it involves using highly digestible phosphorus ingredients, accurately determining phosphorus requirements for specific farm conditions, formulating diets on a digestible phosphorus basis. This is particularly for swine and poultry, and using phytase in a multi-phase feeding program to minimize the overfeeding and underfeeding of phosphorus. But proper diet formulation to optimize phosphorus use efficiency is only one part of the story. It also involves execution, and I made that comment early in my presentation that execution is usually what gets us into trouble. It's not the lack of knowledge or different approaches that we can use. And this applies not only to pigs, but to all animal species. Our goal is to get the right amount of energy and nutrients in the right feed fed to the right animals at the right time. And this can be accomplished by designing feeding programs that use multiple diets formulated to meet the changing requirements of animals, such as for phosphorus, at different stages of production. And in these multi-phase feeding programs, we use feed budgets to help barn workers know when to switch from one diet to the next in the sequence for a specific group of animals that are being fed. And these are really important nutrition practices to minimize cost, as well as optimize animal performance, while at the same time minimizing overfeeding and underfeeding of nutrients throughout different production phases. Feed processing, such as reducing particle size and pelleting diets, improves phosphorus digestibility by 19 to 29%. And we have to remember that properly adjusting feeders to minimize feed wastage can substantially reduce the amount of phosphorus that ends up in manure, not only for swine, but other species. I want to just pause here and just emphasize there's another part of the story that we usually don't think about, and I think it's having significant implications on our phosphorus management story, and that is there are some unintended consequences of feeding biofuels co-products such as distillers grains and soybean meal that are contributing to excessively high amounts of manure phosphorus and nitrogen content. And let me just spend a few moments explaining those. It's become a common practice to feed high amounts of wet distillers grains to beef feedlot cattle. In fact, about 41% of the 33 million tons of distillers grains produced here in the U.S. is fed to finishing beef cattle because it's a widely available and economical ingredient, and it contains more energy value than corn. The high energy content is one of the major drivers of feeding high amounts of distillers grains to cattle because one of the nutritional goals of feeding finishing feedlot cattle is to maximize energy intake. So as a result, it's common to feed distillers grains up to 30% of dry matter intake, but we end up overfeeding protein or nitrogen and phosphorus, which ends up in the manure. So if we compare the amount of phosphorus in manure produced from a feedlot steer consuming a nutritionally adequate diet with no distillers grains, uh, with the amount of phosphorus produced from a steer that consumes 30% of their daily feed intake as distillers grains during a typical 5 to 6 month feeding period, it would amount to almost 4 pounds more manure phosphorus per head compared to not including distillers in their diet. So if we assume that a feedlot has a capacity for 1,000 head and goes through two groups of cattle per year, uh, about 12,200 pounds of manure, phosphorus would be produced if no distillers grains were fed compared to 19,800 pounds of manure phosphorus if we fed diets containing 30% distillers. And this is a difference of about 7,600 pounds more phosphorus that must be applied to cropland when feeding cattle 30% distillers diets. And unfortunately, the potential solutions of transporting manure longer distances to apply to soils where phosphorus is needed or reducing the amount of distillers grains fed to feedlot cattle, these are not practical alternatives to help us deal with this problem. One of the things that I'm really interested in, and part of a study that I was fortunate to be part of, was to use bioprocessing technologies to precipitate calcium phytate from thin stillage and produce distillers co-products that contain more moderate and more manageable amounts of phosphorus. And this could be used to reduce and recover phosphorus for renewable fertilizer, and potentially, as we modeled in this study, calcium phytate could displace 13% of total U.S. phosphorus fertilizer consumption. So I think we need to be innovative in coming up with alternatives of how we're going to manage some of these challenges. We also have a similar scenario that's starting to unfold for increasing soybean meal use in swine diets as a result of government's incentives that have been put in place to increase renewable diesel capacity. And the increased demand for fats and oils is creating increased demand for soybean oil, which is encouraging increased soybean production. And the net result is increased production of soybean meal and excess supply relative to demand while exports are declining and prices are falling. And these market-driven factors are now making soybean meal not only an economical protein source, but also an economical energy source, and is resulting in overfeeding of protein or nitrogen as well as phosphorus relative to the pig's amino acid and phosphorus requirements, which of course increases excretion of these nutrients in swine manure. Unfortunately, this scenario is in direct conflict with our goal of what I call environmentally responsible soybean meal use. And I showed you an example of this earlier where reducing crude protein and soybean meal in swine diets with the addition of adequate amounts of synthetic amino acids and phytase can meet all the requirements of pigs and economically achieve optimal pig performance and carcass value. And so, just to summarize, we know how to formulate diets and design multi-phase feeding programs to minimize phosphorus excretion in manure. But we really need to improve on our execution and connecting feeding program management with manure management to improve overall phosphorus utilization efficiency in our agri-food system. Thank you very much.
Great, thanks so much, Jerry, for that presentation. We had some great questions come in while you were uh, while you were presenting, so we're going to go ahead and answer a few of those. The first one we're going to answer, as Olga is changing them right now. Let's start with this one. If pig farmers use feed strategies such as adding artificial amino acids and enzymes to reduce the amount of phosphorus and nitrogen the pigs excrete, how does that affect the cost of raising pigs?
It's a good question. I I think I may have mentioned it during my presentation, but one of the reasons that phytase use has become so widespread throughout the US and for that matter, all major swine and poultry producing areas around the world is that it's economical. Um, the amount of phosphorus release that we get from adding phytase um, is at least a break even, maybe even a benefit compared to the cost of adding supplemental inorganic phosphate supplements to these diets. So phytase essentially replaces the need to add expensive inorganic phosphate supplements to pig and poultry diets. The business about synthetic amino acids, again, it's a fairly cost-effective strategy, maybe less so as soybean meal prices decrease. But synthetic amino acids are relatively inexpensive, especially lysine, methionine, threonine, and to some extent tryptophan. When you get into some of the other branch chain amino acids like valine and isoleucine, they're a lot more expensive, but we don't need very much of these to balance these diets. So it's a pretty cost-effective strategy either way.
Great, thank you. Second question here is many poultry and swine producers have no control of the feed being delivered to their farms. Do integrators use phytase and other technologies in their feeds to increase phosphorus use efficiency?
Another good question. Yeah, the integrators, I know many of the nutritionists that work in integrated swine or poultry operations, and they do routinely use phytase because it is economical, and many of these integrated operations are they have certain sustainability requirements they're trying to achieve as a company, and so phytase becomes a key part of those strategies.
Okay, and we just have time really for one or two more here. So is phytase an issue when soy meal is used as a fish ingredient, fish feed ingredient? So this is regarding digestibility.
Yeah, so another way to think about this is that any animal species like pigs, poultry, fish, which are what we call monogastrics, uh, do not have the ability, unlike cattle or sheep or goats, to degrade or convert phytate into digestible phosphorus. So in monogastric diets, phytase really helps improve the digestibility by breaking down that phytate into digestible forms that fish can use.
Okay, great. We have a couple other questions, Jerry. I'm going to put them and leave them in the Q&A. If you could answer them sort of as the next presentation is going on, that would be great. I just want to make sure we get all our presenters in before time is up. So I'm going to now move over to the next presentation, which is from my friend and colleague, Dr. Becca Munich. And let me go ahead and share that screen. Sorry, I think you should be seeing it now. Um, so Becca, I'm sorry. Yeah, Becca, you're next, right? Not Mahmood.
Yeah,
That's great. Yep. So Dr. Becca Munich is a watershed modeler focused on surface hydrology and water quality, especially in agricultural ecosystems. She focuses on evaluating the impact of land management decisions within the food, energy, and water nexus. So Becca, feel free to take it away.
yeah. Thanks, Matt and Mahmoud, for inviting me and organizing this webinar. I'm going to just share my screen. And yeah, I'm going to kind of continue. Jerry really set up the problem nicely for what we're all kind of discussing, but I want to really go into what we know about phosphorus flows, and I'm going to focus a lot on manure, but I'll also talk a little bit about some of the other major flows because this forms the basis of all of our motivations and strategies for managing phosphorus. So I just want to talk about what we do and don't know about these flows. So you've probably seen a diagram like this. This one was created in the STEP Center, but showing just kind of all the different pathways that phosphorus moves through the environment. And the more we can know about each of those arrows and add some quantities, the better. And especially as the scale of our analysis changes, whether we're talking about, one farm and we're looking at the phosphorus flows through a farm versus the entire globe. So I'm not going to go through all of these flows because I'm assuming most of you are familiar with kind of the movements of phosphorus through the environment. But what you'll start to see, and Jerry had a few of these studies in his presentation, so I'm not going to go too in detail, but you'll start to see maps and things get produced. Like this is a global phosphorus flow, which is focused on fertilizer imports and exports only. So this is really looking at, who's a net exporter of phosphorus versus importer, which is a really important thing to understand in the global phosphorus ecosystem, and really important, as we heard, how much economics can drive what's actually happening on farms. So you'll see studies like this done at a global level. There are lots of national scale studies. This is a different one than the couple that Jerry showed, which really try to look at what's going into a specific area. Maybe like this one is at a HUC scale, maybe it's at a county level, maybe it's at some regional assessment, but try to look at what phosphorus is coming in, what's going out, and what's that net difference, and try to look at maybe over time or space how these flows are increasing, decreasing. These are quite common. You can call them kind of nutrient balances at kind of large scales. But they're really important because they help us to do a lot of things, like identify potential areas of concern. So if we see a lot of extra phosphorus sticking into a unit of analysis, that might mean we have a lot of legacy phosphorus that we need to deal with. And it could mean that we also might see some problems like eutrophication related problems associated with that excess. That excess could also mean there's a surplus, and maybe that's an opportunity for recovery or reuse or better management, which is really one of the things I'm really interested in understanding and improving phosphorus flows, is trying to think about where are those opportunities that we can say, okay, here we might need improved management, which we might hear from Mahmoud in a minute, or maybe technology that we're going to hear later. So if we can really get a handle on these flows and these quantities, we can drive management and opportunities. But what I really want to convey today is all the things that we don't know about some of these flows. And I'm going to briefly go through a couple other flows, but really focus this talk on manure and what we know about where and how manure is getting in and moving through the environment. So I'll just quickly mention, wastewater and industrial phosphorus flows. It's, for the most part, we have a pretty good handle on where these are going into the environment because the EPA requires NIPD's permits, National Pollutant Discharge Elimination Systems permits for facilities that discharge into waters of the U.S. So they have to self-report this data to the EPA, which then also goes into a system that EPA maintains called ECHO, Enforcement and Compliance History Online. So we can get some data from that, maybe how much flows they're reporting, the concentration of phosphorus, but it also really depends on what they're permitted for. And not every wastewater treatment plant in the country is required to monitor and meet certain phosphorus discharge requirements. So it can vary, but we can get some pretty good estimates of where phosphorus is going into our surface waters through this kind of data set. So we know a little bit there. I will also say that, depending on the permit, we may have a monthly concentration, maybe quarterly, sometimes in larger areas, or where there might be, more concern, maybe we can get some weekly to biweekly measurement. So there is a lot of uncertainty even associated with this data. Biosolids and sludge, which are sort of the leftover parts of that wastewater treatment processes. We don't have as much information on what's happening with these flows. There is a US EPA biosolids annual report that is required for certain size wastewater treatment plants. But we might have general ideas about, is this going to landfills? Is it being incinerated? Is it being applied in agricultural systems? But we don't have much on spatial locations of applications. And that can also vary by state. Some states do maintain that information, but those kinds of flows kind of get lost in terms of where all of those phosphorus that's retained in the biosolids and sludge are going. And then another major flow I kind of already mentioned, fertilizer at the global scale. In the US, there are some data available at the county level that really comes from fertilizer sales information. It doesn't really distinguish between the types of phosphorus fertilizers, so MAP versus DAP. And so that can maybe hinder some of our flows and analyses. And it's not spatially resolved because, again, it's based on fertilizer sales. So we don't know, if a farmer is living on the edge of two counties and maybe they get their fertilizer in the county next door because that's closest, but they're applying it in the county they live in, that doesn't always come across in that data. And then, of course, there's no details on the timing or amounts or specific locations of where that fertilizer is entering the environment. So, a lot of the maps you'll see probably don't go beyond a county scale in terms of resolution because it's really hard to get down beyond that. So I want to talk about the number one P flow in the US, which is, colloquially, we call it number two. So manure accounts for over 50% of the phosphorus applied to the landscape. So it's a really important piece of managing the fate of phosphorus throughout the environment. So I want to talk about what we do and don't know about it and where it's entering and moving through the environment. So a lot of the data, I'm going to talk about two major places we can get data on manure flows in the US. I like to always include the word quinquennial. It means once every 5 years. I just think it's a fun word, but the National Agricultural Statistics Service has an agricultural census once every 5 years. And you can find a ton of information. It's a really great resource. It has animal, livestock inventories and sales per county that are self-reported by farmers in addition to a lot of other data. And it's a really great data set because it's every 5 years, goes back to the 1800s. So we have, long record of livestock locations at a county scale over time. However, there's been studies that show there's declining participation in these surveys. So not everyone is wanting to fill out these surveys. And of course, I'm sure all of you know that work with livestock that livestock can turn over and change frequently over the course of 5 years. They might move from, feeder to finishing lots. Broilers and things have a much shorter lifespan. And so while sometimes that sales data can help with kind of filling in those gaps, it doesn't really give the full picture of where livestock are. And of course, again, it's not very spatially resolved because it's at the county level. And in some cases, it may not be available at the county level if maybe there's only one or two large producers in a county of that particular livestock. They will censor the data because they don't want it for farmer privacy reasons. And then I think the biggest thing is that livestock count or sales is not always equal to the manure generated or applied. And, Jerry talked about the importance of knowing feed content, for example, for understanding what makes it into the manure. And we don't really have that coupled with this livestock data. So whenever you see those maps that are, at a county scale or a watershed level, those are based on excretion coefficients that are very general. And there's a lot of uncertainty to that, which Jerry definitely highlighted in his presentation. So another source of data for very large operations can be those NIFTYs permits again. So these would be required for some states, I'll talk about that in a minute, and not, depending on how many livestock are at a facility. So you might have heard the term CAFO, so concentrated animal feeding operations. So some states do require all CAFOs to have a NIFTYs permit, so that same kind of permit that wastewater dischargers are required to get, and some don't. Some do also have state level permits that either might supplement or replace those NIFTYs permits. But I'll talk about that regulatory limitation in a minute. And if you do have one of these permits for a state, you may be able to get those permits through a public records request or a FOIA request, or it may be publicly available depending on the state. And if you do have that permit, you can get the exact location with a livestock estimate. Sometimes there's annual reports to these. It may or may not have field boundaries for where they're actually applying manure and what rates they're applying, and even some measurements of the phosphorus and nitrogen that's in those manures that they have on site. And so some of that information can also come from the nutrient management plans that are associated with these permits. And we've done that. This is a really blurry image, but from a paper where we were looking at CAFO manure application by looking at the data in these permits. So those can be really helpful for drilling down to where exactly manure might be going in the landscape, how much is being applied, at what rate, and to really understand at a higher resolution where the manure is going. However, as I mentioned, not every state requires these permits or requires CAFOs to obtain these permits. There are some legal back and forth that I won't comment on, but there's so just to suffice to say that not every state requires this. And I highlighted where I am in Arkansas, and this is again very blurry, but in Arkansas, the total number of CAFOs per the EPA's federal definition is 776 as of 2023, but none of them have NPDES permits. So again, there may exist some state level permits, which you might be able to get this data, but for a lot of states, we just don't even have these permits to get down to a smaller spatial resolution. And then another thing that has come up is even for the states that do require that these large facilities obtain one of these permits, small facilities typically don't have to get one of those permits, so they tend to fall under the radar. And this can actually matter. We've done a study where we were looking at the clustering of both large and small animal feeding operations in different places across the US. And what we found that was when you had a cluster of a lot of small animal operations in one area, they could have as high nutrient loading as some of the very large operations. So it can matter if you're only going out and looking at the largest facilities in terms of data. Those small facilities can contribute a lot, especially at a local level, to potential water quality issues. So if you want to read more and dive more into some of the kind of limitations of the data that we have available in the US to look at livestock and eventually their manure, we wrote this paper last year and it goes into more detail. But I don't want to spend all the time talking about what our limitations are, so I want to switch gears just briefly and talk about what we're trying to do in our group to address some of these data limitations. So we just published this paper last year. Essentially, one of the big projects we're working on with the STEP Center is we're trying to create a map for the whole US of all animal feeding operations at a parcel scale. And so this is a remote sensing and machine learning based analysis. These are some of the data sets that go into our model. And then for all parcels in the US, we have a predictor to say, is this parcel likely to have an animal feeding operation on it or not? So it has pretty good accuracy. If you want to read more, I'm not going to go into all the details about this paper, but we are trying to move towards a national database that could easily be updated over time because we know that things change. New farms pop up or some close down. So we want to be able to improve these estimates quickly over time instead of having to wait for a census that happens once every 5 years. And so this is some of the results from that, the accuracy and some of the important predictors in that model. So we have this kind of national scale predictive model at the moment. And what we're doing right now is to improve on it is really using that national model to inform some regional models that really help refine our predictions, because all the AFOs, definitely vary regionally. And so we're kind of using a two-step process in that case. But we also are trying to go just beyond just location, because again, just knowing that there's a barn in a place doesn't necessarily mean that we know how much manure is being produced or where that manure is going. So on the left, this is from some current work we just presented at a conference this summer, where we're trying to estimate the total number of animals that are on site within a parcel. And we're doing a pretty good job and continuing to improve this work, but by being able to estimate at least the total amount of animals on site, we can get to a better manure generation estimate, which will help us get more spatially resolved. And then we published the paper on the right a few years ago, where we were trying to use remote sensing approaches to estimate which fields might be receiving manure and how often were they receiving manure throughout a certain time period. And it was a pretty good predictive program. And so these are kind of two examples of some of the things that we're trying to do to really get at better, spatio-temporally resolved manure application estimates. And then finally, I just want to highlight some of the work that our work is contributing to in the STEP Center that's led by Dan Obenauer, my colleague at NC State, where we're trying to go beyond just these nutrient budgets. Instead of just saying there's a surplus here or a deficit here, we're trying to connect those to the actual in-stream concentrations and loads that we see, so that we can have a better idea of what's the major contributor to some of those values. And so this is a paper published last year by Dan's team. And if you really want to explore this data further, I put this link here to our STEP Data Explorer, where you can go in and play around with this data and look at means versus highs, lows. It's a really cool tool. But that's kind of our ultimate goal in the STEP Center. We want to be able to use all of this improved data resolution to improve our models that can try and look at where do we have some real opportunities to intervene with management and technology, because at the heart of our center, we're trying to drive some phosphorus sustainability technologies and management opportunities. So with that, I'll stop, and if we have time for questions, I'll be happy to answer them.
Great, that's great, Becca. And we do have some time for questions, and we got a bunch of them. The ones we don't get to, maybe you could answer in the chat if you would. Let me go ahead and share my screen here. So the first question here is, to what extent does phosphorus input differ from phosphorus output in a watershed? This is a big question, but Becca, I don't know anyone who's better equipped to answer it than you are. Considering soils, phosphorus speciation, fixation, mineralization, crop uptake, runoff, and their variation with crop type, soil characteristics, precipitation, and other factors. And which of these processes most strongly influence eutrophication by driving phosphorus losses to downstream water bodies?
Yeah, that's a great question. And as a good scientist, I'll say it depends. So yes, phosphorus input is definitely correlated overall with phosphorus output, especially if you look at larger scales. But if you start to zoom in a little and you want to get more accurate, there's gonna, of course, all those things that are in there are gonna affect how much that excess or sometimes lack of excess might contribute to higher or lower loadings or concentrations downstream. They're all really important. And we do have models that are more physically and mechanistic based that we use to try and tease these out. But those models are at watershed scale, field scale, because those processes, as you probably know, vary a lot within those kind of regions. So all of those matter, and when they matter and how much they matter can also, of course, vary by space, but also over time, because you mentioned precipitation, even like freeze-thaw cycles can really affect phosphorus and sediment loading. So yeah, it's not a precise answer, but yes, all those matter, and it can change over time and space. But we do have some models that we can try and look at that and run scenarios through that to try and understand when and where some of those things matter more than others.
Great. And relatedly, there's this last question about whether, what the main drivers are in terms of, is soil erosion more of a problem than livestock feed? And I guess your answer there would also be sort of, it depends on context.
Yes.
Yeah. And I think related to this question, there was a previous question about, whether this is something that just needs, do we just need to tweak certain things in order to fix these issues, or is this a real systemic issue that we need to rethink our whole production system in order to address?
Yeah, I think there are some definite things that might be more blanket. Just the recoupling of crop and livestock systems, of being able to better utilize that manure in crop systems, which currently we don't do a great job of utilizing that manure. I think a lot of that is goes back to Jerry mentioned economics, and depending on how much fertilizers are, manure, and applying manure versus applying fertilizer, and maybe Mahmoud can talk more about this than I can, but has it's a lot of different equipment, or it has some other concerns coming with it. So there are reasons that farmers may not want to utilize that manure in their cropping systems. But that's where I think in steps we're really interested in trying to figure out that problem, and that's one of the reasons for this larger model, is to really drive, like, okay, are there certain places where one kind of technology might be better versus maybe changing the management up a little, and really trying to understand at a smaller scale those processes that are driving losses or issues, so that we can better target our actions.
Great, thank you. And I think, Becca, I'll just ask you to address the next issues and the remaining issues in the chat, if you would, just because I want to make sure we have time for all of the presenters to present. So thanks so much for your presentation. And I'm now going to move on to our next presenter. And that's Dr. Mahmoud Sharara. His research focuses on investigating pathways for the sustainable management of agricultural waste and byproducts to generate value-added products and reduce agriculture-related impacts on ecosystems. Mahmoud, thanks so much for joining us.
Thank you, everyone. I appreciate the audience, obviously, and my colleagues Jerry and Becca setting up the conversation today. I'm Mahmoud Sharara, and in addition to being associate professor here at North Carolina State, I also lead the Animal and Poultry Waste Management Center. And I will I'll present to you today a little closer insights into what happens on the farm. I chose those pictures on the slide you're looking at to give you an idea of different forms of phosphorus in manure in different stages. So left to right, you're looking at a swine farm with a liquid storage structure or a lagoon with a residual solid buildup visible there. Transitioning to the middle picture showing a solid liquid separator with a solid fraction of manures being built up. Those are typically common in dairy farms. And finally, on the right hand side, this is actually a recent good story to share with the group here about innovative technology for concentration and export using drying technology. So the forms of manure on farm vary drastically depending on where you are and the species. I think that's the common theme, is the variability. This is briefly sort of the outline. I'd like to kind of systematically bring everybody to the same background. Manure nutrients, how much nutrients are there? What do we know about it? The typical challenges that producers on the ground have to face when managing manures. The scale question, which was addressed really well in Becca's talk, and looking into the technologies and how its role it can play to actually address this issue. And I've spotted a comment about the distribution problem, whether manure is a distribution problem, and you may find an answer at the end of the talk. So I'll start us with the standard. So what I'm showing you right now is a table showing as excreted value. Again, we can't definitively know how much nutrients each animal or species is excreting. However, we know roughly based on data of researchers and nutritionists, studying these systems, the amount of nutrients that are excreted by each animal. And that's a standard maintained by the American Society of Agricultural and Biological Engineers. The amount of nutrients excreted, however, are not exactly the amount of nutrients that are being land applied or managed on an annual basis. That's mainly because between excretion and actually application on the field, there is storage, treatment, and management that can result in accumulation on farm, losses, and that's where the regionality and the impact of the species play a really huge role. And that's one of the key important things to keep in mind where the farm is and the species, to think of the opportunities and the solution. And as an example, I'm showing here a picture to a typical swine farm in the southeast here in North Carolina as an example, showing the barns, a swine lagoon, manure lagoon to store and treat the manure, and going to an example of a field for land application. The black arrows represent flows primarily for nitrogen. This is excerpted from a fact sheet we've developed with students to really tell the story of nitrogen flow in an animal farm. It holds as well to tell the story of phosphorus with some adjustment, primarily the volatile forms we don't see in phosphorus as we see in nitrogen. But we really see that there is some storage that happens in the lagoon. We see routine application. Some of it is used to flush. So for instance, if we're applying the manure on a nitrogen basis, as you might imagine, we might be managing much lower amount of nitrogen compared to what was excreted because of the volatilization in barns, in lagoons, and in field application. So realistically, we start to look closer at the as applied data. And this data are maintained on farms individually or aggregated by labs that conduct these analyses to growers to inform application decisions. I want to kind of highlight a project out of the University of Minnesota that really worked to aggregate data from a lot of these labs on a national scale to build a manure database. And this manure database really looks at different species and regions, and allows you to really do a lot of research to conduct this, to build a figure similar to the one you're looking at right now, that you can look at a beef manures, for instance, that are managed as solid compared to liquid, and the amount of nutrients in pounds per tons or per 1,000 gallon. Primarily the macronutrients we're always interested in, that is nitrogen, phosphorus as P2O5, and potassium as K2O. And those ultimately are the primary decision nutrients that growers land apply based on. When growers typically have to make the decision based on the crop needs, and on the figure here on the left, those are the solid black boundaries, and the amount of nutrients in the manure, which are the colors. And I want to highlight, many of you may be familiar with that already, but here applying manure on a nitrogen basis to meet crop demand means that there is a surplus of phosphorus here, the yellow that is spilling out of the phosphorus dark box, simply because of the ratio of nitrogen and phosphorus in manure are not matched to what crop needs. So ultimately, using manure as a nitrogen source implies a buildup or an accumulation of phosphorus in these soils. Or alternatively, using manure on a phosphorus basis implies having to purchase additional fertilizers. So that's primarily additional nitrogen and potash to meet the nutrient crop demand. So really that trade-off becomes the decision for growers. And not visible in that choice also is the added acres that will be required to manage manure on a phosphorus basis compared to nitrogen basis. And that's really gets us to the point Jerry mentioned at the first talk, which is the concentration, spatial concentration of animal operations and units on the landscape relative to cropping areas. So that distribution creates that trade-off or choice for us. So when we look into the concept of balancing, we can really apply it at different scale. And we are familiar with the 4R typically that are used to guide growers to rate, timing, placement, and form to inform the management of nutrients. And we recognize that we can't really supply only what the plant removes. There generally is a buildup or what goes in the soil stock. The issue happens when there is a gradual, continuous, and sustained buildup and contribution to that soil stock, especially on animal operations where there is that surplus, if you will, of phosphorus there. And it continues to play out at even larger scale until we move to a watershed level where all of these factors start to play a role. So the use of the water boundaries or the farm boundary or even field boundaries are all important for various levels of decision. Smaller scale, we can make a lot of critical decisions for an individual farm. As the scale grows, we start to see the multiple stakeholders are present and the challenges of actually orchestrating everything happening on the landscape. So really, one of the studies that we've conducted try to take this balancing on a national scale. So this map has been the study conducted by a national team of the USDA looking into building what they called manure sheds, which is basically where manure needs to be land applied to be assimilated by crops. Green highlights counties where nitrogen can be accepted for application or phosphorus. And dark brown represents counties that actually can act as a source to distribute beyond their boundary. Essentially, they can meet internal demands and export. And we see these same hotspots in the Southeast, Northwest Arkansas, Central Valley in California. And one of the critical questions here, myself and my team, we started to ask on a regional scale, how can we refine this data better to start to look into our, not just counties in the state or in the Carolinas, but specifically on river basins. So really our question was trying to answer, we have better idea based on permitting data on where animal operations are. So can we use this data to actually build a watershed-based nutrient balances? And what can we learn from these balances at varying hydrologic boundary scales? So this gives you a visual of that Eastern North Carolina concentration of both swine and poultry production in North Carolina, and some distributed across 5 river basins. Primarily concentration here is in the Cape Fear River Basin and in the Neuse River Basin. And a key critical point that I want to highlight here is that if we looked strictly at the amount of nitrogen an animal excretes compared to the amount of nitrogen crops require, we'll find that we actually have some surpluses here, as you can see highlighted by the dark brown colors. However, if we looked only at the nitrogen as applied or as managed, it's actually, the picture changes drastically. We actually start to see less of an imbalance. That is really indicative of the losses that we see sustained during excretion and storage in the farm, as well as during transfer and storage in lagoons and stockpiles. So we know from the balance of nitrogen to phosphorus crop requires, our phosphorus really stays the same. So we saw some sub-watersheds that show hotspots of phosphorus imbalance or enrichment across the landscape. And that picture does not really change much between phosphorus excreted versus phosphorus as managed, simply because most of our phosphorus is conserved. And what that leads us to is this critical point of spatial aggregation. So looking from the left to the right, we are moving a scale up into the spatial extent from hydrologic 12 boundary all the way to HUC 6. And what we're seeing is that the imbalance or the accumulation of phosphorus actually starts to be averaged out as you move from these levels and stopping at the county scale and keep moving upwards. So we may have a basin level balance that looks okay or maybe slight a build-up, whereas most of the challenges are really highly spatially concentrated. So we really need to be acting local or super local, especially when we're trying to address these imbalances of phosphorus. This really gets us to shifting into the technology. What is happening on farms? So I want to start by an example of some technologies that we are working with, and my colleague Jeff will talk in detail about technologies. But I want to highlight a study conducted with colleagues in Wisconsin looking at dairies. And what you're seeing here is an example of a dairy farm, starting from the upper left where the animal excretes the nutrients. They can enter a digester to produce methane and biogas, and it can flow into a different unit operations, separator to separate solids and liquids. Our solids primarily carry most of our phosphorus, so that technology alone can really help us partition phosphorus better and improve its management. We can further, on dairy farms in particular, that could be further dried and could be used to rebed the animals or could be exported. And the liquid could be directly stored after the digestion. The driver for a lot of the management on dairy farms, especially digesters, is carbon and carbon credits and greenhouse gas reductions. But what I want to highlight to you is the impacts of these technologies on phosphorus. So strictly separation technologies across 9 farms that we assessed in this study, we saw that the solid fraction captures phosphorus, which is the total phosphorus or the in the blue squares here. Depending on the effectiveness of the separator, can captures between 20% and 70% of the phosphorus in the manure into that stackable solid form of manure that could be trucked or transferred longer distance, which can really create a very effective form of long distance distribution or redistribution of that manure phosphorus. Not only that, but because of that separation technology, we're actually seeing an alignment between phosphorus ability to redistribute phosphorus and the farm-wide greenhouse gas emissions. So the picture here on the left is showing the greenhouse gas emissions for a raw manure as managed, a total by the diamond, green diamond at the top. And progressively, as you're moving right, you're introducing technologies, whether a digester or an anaerobic digester AD, a solid liquid separator, or an anaerobic digester plus a solid liquid separator. So we're seeing an alignment to where installing these technologies or stacking them can actually affect both greenhouse gas reduction as well as an opportunity to concentrate the phosphorus into an exportable form. A similar study, and I want to highlight here, and is looking into the sludges that accumulate in these lagoons over long time or continued operation. So out here in the southeast, we rely on these manure lagoon liquid treatment, which is a liquid structure. Over 10, 20, 30 years of operation, solids accumulate, and you can imagine the amount of phosphorus that build up is quite significant. Conventionally, this material is managed following that S1, the blue arrows. So it's slurried, moved in tankers and land applied. That practice typically is reserved for moving that material no more than 2 miles to 3 miles from the farm. So immediately you can draw a very small circle around the farm where that phosphorus ends up going. At some point, a new technology was added to actually add a polymer and a bag filter, which is what you're seeing under S2, that can dewater it to a degree and transfer it for land application. More recently, and some of our research is actually looking into using an excavation type management, where this material can be removed, as you can see from S3, and further dried in drying structures. And here in the southeast, because of our temperatures, using greenhouse or passive drying systems can actually leverage this thermal energy to affect the drying. So as you might imagine, from a cost perspective, if you are managing manure on your farm, on your acres, you're most likely going to manage it as a slurry, S1. The question starts to arise, if we want to transfer this material long distance, which of these options will be the most economical? And what we're seeing in this figure is the results from that work, which is as you start to transfer manure, the horizontal represents kilometers from the farm, you quickly see a clear winner as we start to go over 120 to 130 kilometers, which is to excavate and dry this material and then transfer it for land application. So it has a higher cost initial on the farm, but the incremental increase with the transportation is actually much smaller compared to the other technologies. Not only that, but I want to highlight to you that those black circles that you are seeing here, that shows you clearly how rapidly the cost increases if manure is simply being transported as a slurry or a liquid. And that's the reason why, like Jerry indicated early, manure doesn't move often very far from the farm. And it's only when we affect this separation or processing technology, we can affect a better redistribution. Not only that, but when we look into the greenhouse gas impacts of these different technologies to manage this material, we find that it can continue to be actually net negative when you are comparing it to the value of replacement phosphorus fertilizer, considering that it does not come with an upstream greenhouse gas emissions as a manure or a waste byproduct. So this particular technology, and one of the better success stories is we're seeing a broader adoption, a growing adoption here in North Carolina. And we're looking to share more updates with the wider group here on this technology. But really, it helps sum up a lot of the work myself and colleagues, and maybe set the stage for Jeff's conversation. The characteristics of the manure are really farm variable, species variable. The decisions about balancing the different nutrients carry economic and logistical considerations. Understanding the hotspot is critical, and where it is can help inform the technology selection and the economics of which technologies can be economical to implement. With that, I'd like to pause here and look at any questions that you may have for me.
Great, thanks so much for that, Mahmoud. Unfortunately, we don't really have time for questions, but there are some in the chat there. If you wouldn't mind addressing those while Jeff gives his presentation, I want to make sure that there's enough time for him to present. And so I'm
Sure.
going to go ahead and introduce Jeff. Jeff, I'm going to advance your slides for you. Jeff serves as a technical consultant for Nutrient. His main responsibilities include the review and evaluation of innovative dairy-related manure management technologies. And he recently retired from USDA NRCS, where he served as the leader of the National Animal Manure and Nutrient Management Team. So Jeff, I'll go ahead and advance your slides. Just tell me when you want me to move that.
Sounds great. Now let's go ahead and advance the next one. Again, I want to thank all of you for the opportunity to share with you today. I've spent the last almost 40 years now dealing with manure management related types of issues and really getting into it pretty heavily the last 25 years. So we're going to be looking at this whole phosphorus issue. Like, where did it come from? Where's it going to? Those are just, we're going to try to address some of those. Let's go to the next slide, if you would, please. So through this presentation, what I hope to do is for us to understand as a group the distribution of the nutrients in the manures, because that's going to really impact, if you need to do some type of a technology, a unit process on those manures, how you're going to do that. I know we've seen a lot of maps about these hot spots. I just want to spend just a moment or two on those, and I will spend the bulk of my time today talking about some of these various manure management technologies for partitioning phosphorus. Because one thing we need to understand, we're not removing nutrients, we're partitioning so we can determine what we're going to do with those nutrients. Because as Mahmoud just mentioned, phosphorus is pretty stable. It doesn't volatilize, it doesn't move that much, except for maybe in storage and some of those types of things. It doesn't do like nitrogen. It's not volatilized. It's not as mobile as your nitrogen and some of your other nutrients. Let's go to the next slide, if you would, please. So again, looking at the properties of phosphorus, and we've already touched on this, phosphorus tends to attach to manure solids. So that's where you're going to find the vast majority of your phosphorus. And the thing is, when you look at some of these technologies, the actual highest amount of phosphorus, percentage of phosphorus, is going to be in your fine solids. And that's where things get a little trickier, is how you're going to address that. Also, since the manures, the phosphorus tends to attach to manure solids, and then also I would just say solids in general, for land application, if you have an erosion, and this has been touched on as well, high erosion rates, you're going to have a tendency of your phosphorus to be moving into your water bodies from those erosion efforts. We've also seen some of those areas where you have extremely high levels of phosphorus in your soil. It actually can get into a soluble state, and we've actually seen some of that phosphorus begin to leach down towards the groundwater when those levels get extremely high. Let's go to the next slide, if you would, please. So this is kind of the basis of where we're going today. When we're looking at those animal species that produce both urine and feces, this is the general breakdown of these three main primary nutrients. From a phosphorus standpoint, 90+% of the phosphorus is found in the feces. And that's really important because your feces, that's your solid component. And that's where we're going to be looking at some of these technologies to try to get more of that phosphorus out. Whereas potassium, you have 80 to 90% is in the urine or in the liquid phase. Now with nitrogen, you do have about a 50-50 breakdown. But what I will say is that you have organic nitrogen in your feces and inorganic, which is plant available, in the urine. So let's go to the next slide, if you would, please. You've seen all kinds of maps. I don't want to spend a lot of time on this, but notice the manure phosphorus levels, how they have, they tend to be regionalizing. And if you follow I guess you just follow where the phosphorus comes from, you're generally going to see this relates very well with those concentrated animal feeding operations that have been mentioned so much here in these presentations. And so how can we address that? How can we deal with these areas where we have these concentrations of phosphorus and address those? Let's go to the next slide, if you would, please. So some of the studies that have been done, we see that farm level, that's where the production of the manures take place, the immediate area around the farm. Back in 2007, they were saying that the excess farm level excess phosphorus was about 829 million pounds. Well, 2012, that number went up. So, but when we look at a county level excess manure, and that's just looking at a county, how much manure, how much phosphorus is actually land applied within that county, we see a similar trend. We see that number is on the increase as well, going in 2002 to from 146 counties to 205. So again, that number is going up. Now, is that always bad? No, because one thing I do want to mention, that just because you have excess phosphorus within a county, within a farm, that does not mean it's being mismanaged. It just means, what are they doing with it? How are they managing that phosphorus? How are they managing that manure? And that's kind of where we're looking at some of these different technologies be coming up. And there was one of the questions that came in, and this was kind of my one of the things that I have talked about for many, many years. We have plenty of land to spread animal manures on. I truly believe it is a distribution issue. How do we get those manures from that area of high concentration of animals to the area of low concentrations? And Mahmoud kind of touched on that a little bit with that drying process where you go up to, a couple 100 kilometers and maybe still be economical. And we'll talk about some of those other technologies as well with that. Next slide, please. All right. The bulk of the presentation now is going to be looking at these removal technologies. I'm going to look at physical processes, chemical processes, and biological processes, and see how we might be able to address some of these phosphorus issues. Next slide, please. Okay, first looking at physical processes. Here we see, now this is actually I guess I'll call it a pre-physical process. This was some work that was done at NC State several years ago, where they used a pre-separation manure belt. And remember, in that one slide I showed where the phosphorus was and where the nitrogen and the potassium. Well, with this belt, what the goal of this belt was the solids stay on the belt, the liquids roll off of that belt. So here, there is not only doing the separation or the partitioning of the phosphorus, the nitrogen, and the potassium, but there's some other benefits from this as well. Let's go to the next slide, if you would, please. So again, the liquids are separated from the solids. The liquids flow off the belt, and the solids remain on the belt, and then they would go and they would be processed at another location. Again, you're going to have 90% of your phosphorus without having to do any type of separation. 90% of your phosphorus has already been separated through this process of just preventing the liquids, the urine, from combining with the feces. Also, another benefit is that because the urine and the feces do not combine, you're having that a limited bacterial interaction. So you're reducing the ammonia, you're reducing the carbon dioxide emissions, and you're also reducing odors. With this, you're getting less water usage, And also with that, you'd have less liquid storage volume required. Next slide, please. So let's look at some coarse and fine solid separation technologies. Next slide. All right, this was a study we did back in Colorado a couple years ago, and we had an incline screen. This is on a dairy incline screen, which was in line with the centrifuge. If you look at this, the image of holding the manure here, notice the material on the right that came off the incline screen. See how much lighter that color is. See how much larger the particle sizes are. There you were seeing that the centrifuge, which is able to get a much higher percentage of the solids and also able to get much finer solids, they were able to get 4 to 5 times the phosphorus with the centrifuge as they were with the inclined screen. Next slide, if you would, please. This is another study that we looked at. This actually had an anaerobic digester sign associated with it. Here we had screw press. The liquid from the screw press then went to the centrifuge. We see here the coarse solids, which came off the screw press. You can see how much the lighter color, the coarser material compared to the fine solids in the background of the image. And here we also see that, again, the centrifuge removed a much higher percentage of the phosphorus than the screw presses did. So again, these are some technologies that can be looked at to remove the solids or a percentage of the solids to get a percentage of the phosphorus. Now, one thing we got to understand that these technologies, depending on the technology, that's going to impact the amount of phosphorus that you're going to be removing from the system. Next slide, if you would, please. This one here is something that's called ultrafiltration, where they're using membrane technology to remove additional solids. So usually you have to have a coarse solid separation technology first, so you do not plug the membranes, and then you would use these membranes to remove additional settleable solids, your fine solids, to get this high phosphorus concentrate, and then you'll have a low phosphorus permeate that could then potentially go into the reverse osmosis, and through that you would remove your nitrogen and some of those types of things. So when we're looking at this, we are looking at different types. Oh, go ahead. They were fine. That's you see there's a difference in the partitioning of the phosphorus. So if you're doing coarse solid separation, such as with a screw press or an inclined screen, you're only getting about potential 15 to 20% of your phosphorus. If you go into fine separation, such as a centrifuge, you're approaching 80%, or I'm sorry, approaching 50% or more of the phosphorus being removed. And then with your membrane technology, you're getting 97, and I've seen upwards of 100% of your phosphorus is being removed by that membrane. Notice here you have a cost associated with each of these technologies, and now these are just estimated costs. We need to understand there could be some ancillary practices and things that have to be added. These numbers can go up or down depending on your particular application. Again, these are just estimates, but notice the more phosphorus you wanting to remove, the higher the cost associated with that technology. Next slide, please. Chemical processes. Go to the next slide. This is one that Mahmoud talked about using the geotextile bags. Here you're using coagulants and flocculants to add to the effluent that's coming from, whether it's a dairy operation, swine operation, whatever liquid-based system you have. You're injecting that into these bio bags, and then it basically filters out. Now you have to use those, either the polymer and or the flocculants, metal salts. You have to do that, because if you don't, then the manure solids will blind the bag, and it will not allow the material to leach out. So it's really important to do that. Again, the cost is extremely variable. Also, we'll say the bag's only used once, because you have to cut the bag open. They just have not found a way of multi-use of these bags yet. Again, a cost of $20,000 to around $75,000 for a single-use product. There are some technologies out there that I've been looking at to potentially have a filter bed to do the same thing that could be reusable. We just haven't moved too far with that system yet. Next slide, please. This is another system, an alternative to, I guess I'll say, an alternative to the ultrafiltration, in that you can have a polymer addition after you've done your coarse solid separation. Put polymer addition in. From that polymer addition, the solids settle out, and you can use a screw press to remove additional liquids from that. And from there, instead of having a liquid form of the high phosphorus, you now have your high phosphorus in a solids form. Again, we see the cost associated with this. The more phosphorus you're trying to get out, the higher the cost is going to be with the operation. Next slide, please. So again, chemical enhancement, a couple of things. You're going to create flocks. You're going to take those little bitty particles and you're going to clump them together. Makes it easier to capture that phosphorus. Phosphorus removal rate can be 75% or more. I've seen upwards of 90% or more. One thing to note, by using mechanical dewatering technologies after the polymer addition, it can lower that removal rate, because you have a tendency to break those flocks, and it may actually be removed from the solids. Just like with the membrane, you could potentially apply other technologies like reverse osmosis and get you even finer solids removal, better quality of liquid that you're dealing with following that technology as well. Next slide, please. Underneath the chemical process, I also include thermal chemicals such as combustion, gasification, pyrolysis. These are different technologies depending on the temperature that you're operating these at, depending on the amount of oxygen that you're using within the systems. And with those, you have different emissions, you have different issues depending on those temperatures and oxygen amounts. You're also going to get different types of products being produced. You're going to get biogas, or I'm sorry, syngas. You're also going to get bio oil, and then also char or ash, again, depending on the technology that's being used. Next slide, if you would, please. A study that we actually just wrapped up in New York. We were looking at this particular pyrolysis unit. It was producing biochar, and we were getting at least 10 times the increase of phosphorus from the manure solids that have come off of the screw press that we're using on this particular system. So we get a huge concentration of the phosphorus, and by getting this concentration, this, I think, applies back to what Mahmoud was saying. We can now take this product, which is high phosphorus. Now, I will say it's going to be fairly low in nitrogen, because you lose a lot of the nitrogen through the volatilization process. But the nice thing about the pyrolysis unit, it's usually being emitted as N2 gas, not as any of the NOx that we have with some of the other processes. So here we can take this material and send it a much farther distance than with your traditional, just your separated manures. Next slide, please. So again, we can reduce the manure volume up to 90%. It concentrates that phosphorus, and depending on the process, the temperature, we can see here some of the different things that are emitted. Again, pyrolysis primarily is N2. Here's estimated cost. This varies depending on the size of operation, type of operation, and how you're going to be dealing with the pre-processing before it actually gets into the unit. Next slide. Real quickly, one last process, talk about composting. Different types of composting processes. You have bin composting, rotary drums, windrows. Again, it depends on your operation, depends on what you want to do. Do you have a product that you want to utilize following this? Go to the next slide, just to kind of summarize this. You do get a volume reduction, and through that, you're concentrating your phosphorus. And then, but you also have some emissions that you might need to be looking at as well. Here's the cost, depends on the operational size. Also, it depends on your animal type. Are you adding other carbon sources, those types of things. Next slide. think we're wrapping it up here. Yep. Again, there are many technologies, and I know I went through this extremely quickly. So if you have some time, maybe follow through this this presentation again. But there's a lot of ways of partitioning phosphorus from livestock manure, and if we can get that phosphorus, we get it partitioned, then we can maybe move that further away from those areas of the high concentration phosphorus. But also, there's not one technology that will do it all. We have to look at that. What is going to what are the producer's goals and objectives to remove that phosphorus from that manure liquid stream? That's one of the things you have to look at to address those issues. Also, many of these technologies have significant cost. Are there some potential payment rates or some cost savers out there? I know NRCS, through their payment schedules, they have some potential monies to help with that. There's also some carbon crediting if you're able to get out, some of the carbon from the system. You might be able to get some carbon credits to get some additional funding through that. So there are some revenue streams out there, but that's just some things you'd have to look at. Also, what are your products? What are you going to do with this material after you've done the technology on it? Are you going to land apply it? Are you going to try to develop a market for some of the other things? So that's just something you have to think about. Real quickly, if you have questions about any of these technologies and others, you can go onto the Nutrient website. We have a solutions catalog, and in that catalog, we have over 500 technologies, services, and things that we have evaluated, we've looked at, and you can kind of look at those to see if they can help you. There's some resources in our library. One last slide. You can go. Also, we have currently undergoing a 2020 CIG project, and many of these projects that I presented here today, we've included those on the CIG website, and so you can get an update and kind of get some information about these technologies, how they've worked, and all of those. With that, I'll wrap it up. Thanks for the time.
Great. Thanks so much, Jeff. And I'm sorry, we have some questions, but maybe they can direct them directly to you at the email address that you provided here. We're right at time, so I think we need to wrap it up now. I do want to, again, invite everyone to the Phosphorus Forum, which is coming up next month. You can get to this through our website or through the link that Olga provided in the chat. And I want to thank all the presenters for the time that they've put into putting these presentations together, and thank you, the audience, for attending. This will be up on YouTube probably in a week or so if you want to check it out again. So thanks to everyone for participating.